All right, week 6, and our topic is life cycle analysis. This is all about the energy in our stuff. And we've got lots of stuff in our homes, stuff in our kitchen, our bathrooms, our livings, our bedrooms, our garages. Now, all these things that we've bought required energy to make. Now, those prices for the energy, although typically they're fairly small in Canada because electricity is cheap and gas is cheap, those prices are hidden in the goods. It's part of the price that you pay. Now, at present, it's not an especially large part, but that may change if our energy prices go up, and there's certainly some discussion that our hydro rates are going to go up considerably. Now, the word we use for this is we say that the energy is embedded in the object. Now, that doesn't mean that the energy is actually contained there. So the word embedded energy just refers to the amount of energy it took to make the thing, not any energy that's actually contained in the chemical bonds of the object anymore. Now, this energy usually, well, there's really just two forms of this energy. There's either fossil fuel energy or electrical energy. So, for instance, if you think about making a wooden table, well, you got to cut down the tree, so you'll need gas for your saws and fuel for the truck. You got to transport it to the mill, so that's more diesel fuel, fossil fuel. You've got to saw it up to make furniture, and typically that's provided by electricity. In some cases, that electricity is generated on site, though, by burning wood, and they'll have their own little generators there to make electricity from that. So they'll have a boiler and they'll make their own electricity. Then you've got to transport it. You've got to move it around the plant, and again, there's electricity involved, and there's machines for lathing and finishing the wood. Then, of course, you've got to assemble your table, and typically that involves other ingredients like metal fasteners or brackets. There'll be paint, and that's refined petroleum. You'll pack it in a box. Again, that's made from trees. Then you got to ship it, so that takes more fuel. Then you've got to display it in the store, and that takes both electricity and natural gas. Then you've got to bring it home, and that takes gasoline. And then you've got to assemble it with those tiny little Allen keys, and they're made of metal. So again, all of this takes energy. And anything that you buy has an embedded energy. That's the energy that it took to make the thing. All the raw materials, and to make all the raw materials that go into the object. Now, in some cases, it's surprisingly large. For instance, the energy to make a computer, because of the energy requirements of making the silicon, which is the basis of the computer logic chips, it could take about 4 gigajoules to make a computer. And that's enough energy to drive 2,000 kilometers in your car. Cars also take quite a bit of energy to make as well. Now, the process of tallying up all of this embedded energy, this is known as life cycle analysis. Now, in life cycle analysis, you also compute other things like the amount of water that's used and the amount of carbon dioxide that's produced. But for our starting point, when we say life cycle analysis, at least for the first half of the course, we're just referring to an energy analysis. How much energy did it take to make the thing? So here's an example. We're going to look at the cradle to grave energy signature of a tea kettle. So this is my tea kettle at home. It's about 1,000 watts. And I use it to boil water about twice a day, about 3 minutes of boiling time each time. And I'd estimate that kettle's going to be good for 8 years or so. So for the usage energy, the energy that's consumed in actually using the appliance, well, we've got 365 days in a year, and then we're using it, only once a day. I said twice, but really only once. And then each time I use it, the 1,000-watt kettle, 1,000 joules per second, is on for 3 minutes, and 3 times 60 is 180 seconds. So unit-wise, days cancel out, use is dimensionless, seconds cancel out, and I get joules per year. And if I convert that into megajoules, I see it's about 65.7 megajoules to use it per year. So if you multiply all those together and then divide by 10 to the 6, which is mega or million, you get 65.7. Okay, so that's the usage energy. Next, we're talking about cradle to grave. We've got to actually make this thing. Transportation is a factor in that. So let's say the raw materials, the steel and the petroleum to make the plastic, and the minerals that we need to dig up to make the heating element. Let's say they travel about 1,000 kilometers rather from the ground to the assembly plant, and then another 1,000 kilometers from the assembly plant to the store. And then finally we drive them home 5 kilometers. Now, the cost of truck transportation is, as we gave earlier, was 3.2 megajoules per ton kilometer. That's average value for Canada. So for every ton moved a kilometer, there's 3.2 million joules. We have a 1.2 kilogram kettle if we add up the steel and the plastic and the carbon that go into making it. So we've got 1.2 kilograms. The cost of transport is given in tons, so we're going to divide by 1,000 to convert kilograms to tons. And then we got a total of 2,000 kilometers here. We got 1,000 kilometers for the raw materials to be assembled, and then another 1,000 kilometers to finally reach the store. So that's 2,000 kilometers of truck transportation. And multiplying that all out, we get 7.68 megajoules of truck transport. That takes the stuff from the ground and delivers the product to the store. And then we said about 5 kilometers to drive it home. Driving a car in Canada on average is about 3.7 megajoules per kilometer. We'll drive about 5 kilometers in our car. Oh, so this is car transport. Probably got it over here, don't I? Yes, I do over here, sorry. So there is 5 kilometers in the car. And that works out to 18.5 megajoules. So now our total transport, we've got to add the truck transportation energy to this car energy. And so that was the 7.68 megajoules plus the 18.5 megajoules. That gives us a total transportation energy of 26.18 megajoules. So that's to bring all the raw materials to the respective factories, assemble steel, the plastic, etc., send that to the assembly plant, put that together, and then ship the kettle to the store. Now, of course, that is the total transportation energy for a kettle, but in terms of per year, we only have to do that once every 8 years because that's how long the kettle lasts. So if we divide by the 8-year lifetime, on a per year basis, we find that transportation energy is 3.2725, or about 3.27 megajoules per year of transportation energy. Next, let's think about the manufacturing. We said there were basically 3 components to this kettle. There was the steel body, there was the plastic base, then there's the carbon heating element. So in our model, each of these raw materials has an embedded energy in it. So this is the energy to mine the iron ore, crush it up, and then sinter it, and then cast or roll the steel, clean it up, ship it to the plant where they're actually going to make the kettle. Okay, these values have been tabulated. They're in databases. I just pulled them out of a database. So for the steel, it takes 32 megajoules to make a kilogram of steel. Now, in our kettle, we had 750 grams, or 0.75 kilograms of steel. So that means to make the steel in our kettle, it took 24 megajoules. The plastics take quite a bit more energy because you've got to get the petroleum out of the ground. Then you've got to refine it once it reaches the refinery. Now, the transportation of these raw materials, we took into account already in our trucking energy. So this is just the energy to extract them, process them, and make them into what we need them to be. So, plastic, there was 200 grams, that's 0.2 kilograms, so that's a total of 20 megajoules to make the plastic in my kettle. The carbon heating element was 250 grams, or 0.25 kilograms. At 20 megajoules per kilogram, that's 5 megajoules total. Now, these raw materials then, the steel, the plastic, the carbon, arrive at the kettle plant, and there they have to be put together. And I estimated about 8,000 kilowatt hours to make, let's see, where was it? To make 3,000 kettles per month using 8,000 kilowatt hours. So this is per kettle. And then, of course, we want to convert that into megajoules. Remember that there's about 3.6 million joules in a kilowatt hour. So per kettle, you find about 9.6 megajoules. That's a couple of kilowatt hours. So a 1,000-watt device on for a couple of hours, about 2 2/3 hours, 9.6 million joules. So the total there of all of those, the energy to make the steel, make the plastic, make the carbon, and then put the thing into a kettle, that works out to 58.6 million joules. But then again, this kettle's going to last 8 years. You don't have to put out this much energy every year. On a per year basis, it's 58.6 divided by 8. That is 7.325 megajoules per year. Okay, so in the life cycle, we've considered the energy to make it, the energy to transport the various pieces around, the energy to use it. I know I'm kind of going out of order with the life cycle, but this is sort of in order of increasing difficulty level. That's the reason for that. Now, finally, the end of life energy. Let's just say that we're not that responsible. We just chuck it in the trash, and our municipality is not that responsible. Let's say it trucks it to a landfill 200 kilometers away. Well, trucking is still fairly efficient. 3.2 million joules to ship a ton a kilometer. Our kettle is 1.2 kilograms, and we've got to convert that to tons for the cost of transportation, and then we ship it 200 kilometers. So that works out to 0.768 megajoules. But again, we only need to do that once every 8 years. So if you divide this by 8, you get 0.096 megajoules per year, which is about 0.1 megajoules per year. So those are the 4 steps in the life cycle of this product. And here they are here. They're the totals: the production, transportation, usage, and disposal of the object. You see that for this object, most of the energy is actually consumed in using it. So that means to reduce the energy profile of this appliance, you want to try and use it efficiently. That means you want to only try and boil the exact amount of water you need to make your tea. You don't want to fill the whole thing up needlessly. All right, so now let's imagine that we're a bit more energy cautious, and instead of recycling our kettle, let's imagine that we're able to recycle it. So we recycle the steel, the plastic, and the heating element. Now, what that means then, well, it's not going to change the usage energy. It's not going to change the transportation from the ground to the store and to our home. What it does change is the amount of embedded energy in the product. Because yes, it takes 32 megajoules to make a kilogram of steel, but really we're just borrowing that steel. We're not using it up. You still get that 32 megajoule per kilogram steel at the end, provided you're able to recycle it back to its original grade, provided it's not downgraded. The energy cost then of renting that steel is just the cost of recycling it, which is estimated at 10 megajoules per kilogram. Now, with 750 grams of steel, that then is a lot lower than the cost of actually making the steel. So if you can recycle the plastic and it only costs 2 megajoules per kilogram to recycle the plastic, then with 0.2 kilograms of plastic, the amount of energy cost for the product just to borrow the plastic is a lot less than actually making new plastic. Carbon, instead of making the carbon, you just borrow it, and then you use energy to return it back to its previous virgin state. So this is a lot less than the energy we'd calculated previously. Now, there's some simplifying assumptions here, right? This is assuming that you're returning the steel back to its original state. in particular with plastics, that's very difficult to do. And shopping bags are a very low grade of plastic. So this is probably grossly simplifying. It probably really is a lot more embedded energy in there. It's not just the recycling energy. There should also be a term reflecting the downgrading of the plastic, but we're going to ignore that for simplicity. Now, the assembly is still the same because you are still assembling the kettles in the same way. So we had worked that out previously to be 9.6 megajoules. And then if you add that up, the energy to recycle the products, which is the energy to borrow them, you get about 20 megajoules per kilogram. That's a lot less than previously, but it is an 8-year lifetime, 8 years. So that 20 megajoules over 8 years gives you 2.5 megajoules per year of embedded life cycle energy. And if we look at the graphic then, the totals, transportation is the same as before, usage is the same as before. It turns out disposal is the same as before too, because it's 200 kilometers to the recycling facility, and we send 200 kilometers to the landfill as well. So this is a lot less, right? Previously it was up here at around 7.5. Now it's about 2.5. So we're definitely have a much smaller embedded energy in the product, right? So really these two things are what we refer to in the embedded energy. That's the energy to make the object. All four of these together, the production, the transportation, the use, and the disposal, all of them add up to give you the life cycle energy. But in our accounting, we want to make sure we don't count things twice. We've actually already accounted for the usage energy back when we studied residential energy use. This is a kettle. I'm just using energy from BC Hydro to heat up my water. And then the transportation has also been accounted for in our previous chapter, because this is just freight transport moving around the country. And we have totals from the amount of fuel purchased. So we've already accounted for that one. So it's just production energy and end of life energy that are new to chapter 6. But we will consider them always in the context of these other elements as well, so we get a picture of the full life. Because it's important for us to see, for instance, that really it's the usage energy that matters here. So for instance, if you could cut your usage energy in half with a new kettle, then do it. In energy terms, for the planet, it's better, because yes, you're throwing out this old kettle. Presumably you're sending it for recycling. But the production energy to make a new kettle is so much smaller than the usage energy. Cutting your usage energy in half more than pays for the energy associated with making a new one. And these are some messages that we can get by considering the numbers and by doing a full life cycle analysis.